Now we're going to talk about MongoDB. MongoDB is pretty popular in corporate environments, and you might find the need to integrate it with your Hadoop cluster or with Spark or something like that. It's easy to do, so let's go find out what MongoDB is all about, what's different about it, and how to integrate it with your Hadoop cluster. Let's talk about MongoDB next. MongoDB is a popular choice in the corporate world in particular because it is built by an actual corporation that actually supports it as opposed to just being kind of out in the wild and open source. MongoDB's name comes from humongous data. Mongo, humongous, get it? Which is kind of weird because really what sets MongoDB apart is not the fact that it can handle big data, but just its document-based data model, which is very flexible. And we'll talk about that more shortly. So don't let the name fool you. Other NoSQL databases do just as good of a job at managing big data. Where are we in the triangle of the CAP theorem here? Well, MongoDB sits down on the consistency and partition tolerance side of that triangle. So since it does have to deal with big data, partition tolerance is something it just has to do. And MongoDB chooses to favor consistency over availability. So MongoDB has a single master, a single primary database that you have to talk to all the time to ensure consistency. But if that master goes down, it will result in a period of unavailability while a new primary database is put into place. So the big thing that's different about MongoDB is that you can stick pretty much anything you want into MongoDB. Basically, any JSON blob of data you can shove into a document in MongoDB. It doesn't have to be structured. You don't have to have the same schema across each document. You can put whatever you want in there. So here's an example of what an actual MongoDB document might look like. Let's say that we want to store blog posts in a MongoDB database. Well, this is what it might look like, and this is really what it looks like. So MongoDB will automatically give you an underscore ID field that's just automatically appended to your document that contains some unique identifier for you. And that's done because there is nothing in MongoDB that says that you have to have some unique field in your document at all. So within that document, we might have a title, the content of the blog post itself, and then we can have a comments field that contains an array of other documents. So this is an example of an embedded document where we have a document representing a comment that itself contains a name, email, content, and rating. And I could actually have multiple of these embedded within this blog post document. So that's a little concrete example of what a document might look like in MongoDB. Like I said, no real schema is enforced in MongoDB at all. You can have different fields in every document if you want to. Obviously not necessarily a good idea if you want to actually do fast lookups in that database, but you can. You don't have to have a single key value like you would have to have in Cassandra. That's some unique identifier. But you can create indices in any fields that you want. You can also create indices on combinations of fields. So one nice thing about MongoDB is that it's very flexible in how you can index its data to achieve fast lookups on whatever queries you might be doing. Obviously, if you want to actually shard your MongoDB database, which is how they talk about actually horizontally partitioning it so that you have different ranges of data on different servers, then you have to have some unique index to do that sharding on. And we'll talk about that more in a bit. So with MongoDB, you have a lot of flexibility in what you can store in it, but with great power comes great responsibility. Just because you can shove whatever you want into MongoDB doesn't mean you should. You still need to think about what the queries are you're going to be performing on this database and design your database schema accordingly. So make sure that think about what indices you might need for fast lookups for the queries you're going to do. At the end of the day, it's still a NoSQL database, so you cannot do joins efficiently. So you want to make sure your schema is denormalized as much as you can. In MongoDB world, we talk about databases and collections and documents instead of databases and tables and rows. So this kind of gets away from the notion of there being some sort of fixed schema, which is kind of implied in the words table and row. So a MongoDB database contains collections, and a collection contains a collection of documents. So instead of tables containing rows, we have collections that contain documents. Conceptually, you can think of them the same way, but just keep in mind that collections can contain pretty much anything. And the main restriction here is simply that you cannot move data between collections across different databases. So if you do need to reference data between different collections, they do need to be within the same database. If I can editorialize a little bit here, if you go to the MongoDB website, you'll see it's really aimed at more of a corporate environment. And I don't know, it kind of rubs me the wrong way, to be honest. If you look at the About MongoDB tab, for example, it doesn't really tell you anything concrete. It says, with MongoDB, these organizations move faster than they could with relational databases at 1/10 of the cost. With MongoDB, you can do things you could never do before. Wow, that sounds great to, the sort of CTO that hasn't written code in 20 years, right? But for technical people like you and me, not really very helpful. Kind of rubs me the wrong way. But for corporations, this can be a good thing. You want to be able to pay for professional support and have guarantees about support if you need it. So, MongoDB has that sort of service available to it. And at the end of the day, it is still open source, and you can still get the documentation you need as a developer if you just go looking for it. But man, websites like this just really bother me. All right, let's talk about MongoDB's architecture. So the first thing you need to understand with MongoDB is what they call replica sets. So like we said before, MongoDB has a single master architecture, the idea being that we want to have consistency over availability. But you can have these secondary databases that maintain copies over time from your primary database. So as writes happen to your primary database, those writes get replicated through an operation log to any secondary nodes that you might have attached to it. So in this diagram here, we might have a primary MongoDB server that your application talks to. And maybe we have a couple of secondary backup nodes in one data center and a couple of secondary backup nodes in some other data center. MongoDB will automatically replicate those operations to those secondaries so that in the event that the primary goes down, one of these secondaries can take its place. And the way that replication chain works is kind of arbitrary. It actually just tries to figure out which server can it talk to most quickly. Where's it getting the fastest ping times from? So, you don't necessarily have this sort of structure where you have a primary talking to a secondary and another secondary backing up from another secondary. These arrows could be pointing pretty much anywhere in practice. So the good thing, though, is that if that primary does go down, a new secondary can be elected and take its place within seconds. So it happens pretty quickly. You're not talking about massive amounts of downtime in the event of a primary failure. But you do need to make sure you get that primary back up online pretty quickly, because if your operation log runs out of space during the time that it's been down, recovering that primary is going to get a whole lot more difficult. So, you need to make sure that you still have some operational responsibilities to actually get that back up and running quickly. And I want to stress again that we haven't even talked about big data yet. What we're talking about here in replica sets is just having a single monolithic MongoDB server where all of the data sits on that single server, and we're replicating that data to backup servers. Okay, so we're not talking about big data yet. We're just talking about durability and actually having backup copies of a single monolithic MongoDB database here. There are a lot of quirks with MongoDB, and it's something that it does get its share of criticism for. One thing is that you have to have a majority of servers in your set to agree on who the primary is. So you can't have an even number of servers because you can't get a majority. And that implies that you need to have at least 3 servers if you want to have replication or some sort of durability. And that can get expensive, right? Maybe it doesn't make sense to actually have 3 giant servers just to keep your one MongoDB instance reliable. So to get around that limitation, they have something called an arbiter node that you can set up in the place of a secondary node, where its only job is to vote on who the primary should be in the event of a failure. So that's an option, but you can only have one arbiter node in your cluster. So I don't know, it's a little bit weird. The other thing is that your applications need to know about at least a few servers in your MongoDB cluster. So it needs to know about, your current primary and a few secondaries at least, so it can actually ask one server who the primary is that it should be talking to. So that means that if you're going to be changing the configuration of your servers or adding more secondaries or removing secondaries, at the end of the day, you need to push that information all the way up to your applications, which can be kind of a pain. And again, I want to stress that replica sets only address durability. We haven't talked about scaling out to big data yet. If your replica set goes down for whatever reason, your database is down. Okay, so there is a way to set things up so that you can read from secondaries, but generally that's not recommended. So we're just talking about durability here. But one neat thing about replica sets is that you can set up something called a delayed secondary. And the idea there is that you can set up a time delay between the replication between your primary and a specific secondary node. And you can do that as insurance against doing something stupid. So for example, let's say I set up a 1-hour delay between primary and secondary replication, and I do something really dumb like accidentally drop an entire database on my MongoDB instance. If I can catch that quickly enough, I can shut things down and restore from that delayed secondary to get back to where I was an hour ago and restore that information relatively quickly. Let's talk about big data. That's why we're here. So for actually scaling out data across more than one server with MongoDB, we need to set up something called sharding. And the way sharding works is that we actually have multiple replica sets, where each replica set is responsible for some range of values on some indexed value in my database. So this, in order to get sharding to work, it requires that you set up an index on some unique value on your collection. And that index is used to actually balance the load of information among multiple replica sets. And then on each application server, whatever you're using to talk to MongoDB, you'll run a process called MongoS. And MongoS talks to exactly 3 configuration servers that you have running somewhere that knows about how things are partitioned, and then uses that to figure out which replica set do I talk to get the information that I want. So let's take a minute to understand this architecture here. We can have many application servers. These might be web servers on some big web app, for example, where each process of your web servers is running an instance of MongoS. MongoS has some communication with 3 configuration servers you're running somewhere. And these can run on top of other servers you might have. They don't have to do a whole lot of work, but you need to have 3 of them. And from there, can figure out which replica set to talk to actually read or write the information for a given, say, user ID or something that you're indexing on. And that replica set, in turn, can take care of durability and actually backing that data for that replica set up to a bunch of secondary nodes that it can fail over to. Now, MongoS is running something called a balancer in the background. So over time, if it finds that it's actually doesn't have an even distribution of values in whatever field you're partitioning on, it can rebalance things across your replica sets in real time over time. So in this example, we might have replica set 1 that's set up to handle user IDs, from the minimum value to user ID 1000. Maybe replica set 2 is handling user IDs 1000 to 5000, and replica set 3 might be handling user IDs 5000 to whatever the maximum value is. So these can change over time and get rebalanced over time as the need arises. So that is how MongoDB handles big data. You can see it's actually pretty complicated. But, if you actually, to be fair, if you compare this to something like HBase, where you're using something like Zookeeper to maintain these sorts of configuration, it's not that different. Sharding itself has some quirks in MongoDB. So, for example, auto sharding, where it's trying to rebalance things over time, sometimes fails. There's a rather nasty failure mode called a split storm, where it simply cannot split things quickly enough, and it just keeps trying to resplit things over and over and over again, and your entire cluster goes down. It's a bad thing. Another failure mode is if your MongoS processes on the front end get restarted too often, things will never rebalance. So it actually takes a look on each MongoS process over time to see how data is being distributed throughout your cluster. And if you keep restarting it, it basically restarts the clock, restarts the count on those things. So if you are restarting those processes too often, and sometimes depending on how you set up your web server, that might be the case, things won't be balanced properly. So it's very easy to get into a bad state. Got to make sure someone's really keeping an eye on things from an administrative standpoint. You do need to have exactly 3 config servers. And if any one of them goes down, your entire database goes down. And this really isn't any different from HBase, where you have master nodes that are maintained via Zookeeper. So again, we're trading off intentionally consistency for availability. And the other thing too is, like I said before, even though MongoDB offers a very loosely defined document model, it doesn't mean that your document model should be loose. If you're going to be doing sharding and actually handling big data, you still need to think about having some single primary key that is unique to each document that you're going to be sharding on. Now, I've kind of talked a lot about the limitations of MongoDB, but there are some very neat things about it too. So again, the big plus of MongoDB is that it's not just a NoSQL database, but it can store pretty much anything you want. It also has a shell that has a full JavaScript interpreter, so there's a lot of power there that you can do. You can actually run JavaScript functions across your entire MongoDB database pretty easily. It also supports many indices, although you're still discouraged from doing more than 2 or 3 in a given collection, and you can only have one that's used for sharding. But you can actually set up things like full text indices for doing efficient text searches across MongoDB. So again, MongoDB is really a good choice for things like storing, big documents of information or text. You can also have spatial indices where you can actually do searches across, latitudes and longitudes, for example, and try to figure out what database objects actually intersect a given position, for example, which is kind of a neat feature. Another thing about MongoDB that's worth talking about is that they're kind of trying to make MongoDB into a replacement for Hadoop to some extent. So it actually has built-in aggregation capabilities. You can actually run MapReduce code on MongoDB itself. And it actually has its own file system built in as well called GridFS. That's kind of like HDFS in some extent, where it's storing documents within MongoDB and actually chunking those documents up, kind of like HDFS does. So MongoDB's kind of value proposition is in part the fact that for many applications, you might not need Hadoop at all. MongoDB might be all that you need. But if you are integrating MongoDB with Hadoop or Spark or something like that, it's easy to do, as we'll see in a moment. And the good thing is that it can actually leverage some of these features in MongoDB to do things more efficiently. So for example, if we're tying MongoDB to a Spark dataset and you're telling Spark to go perform some MapReduce task on MongoDB, that work might actually get pushed down to MongoDB itself. So it might not actually have to use Hadoop at all. That can actually lead to more efficient data analysis than you might be able to get from other NoSQL solutions that are integrated with something like Hadoop or Spark. And there is actually a SQL connector available for MongoDB, so you can actually write full-blown SQL against it if you want to, but bear in mind, it's still not really a relational database. Even if you have the ability of executing SQL commands against it, you still can't do efficient joins and can't deal with normalized data very efficiently. So with that, we've talked a lot. Let's actually go play around with MongoDB. Let's actually look at integrating MongoDB with Spark and get some data into it, and then we can play around with the data in MongoDB and see how it works from within the Mongo shell. So let's go have some fun.